This lesson is about general polar form, and before we explain what that is, let's go back and remind ourselves what polar form is first. So polar form is the following. When you write a complex number z in this form, or cos theta plus I sine theta. Now, before we start general polar form, we need to take a closer look at the angle theta itself. So this angle, let's zoom in on this angle and have a closer look over here on the side for the moment. So back to some trigonometry. The angle theta, there's more to it than it seems, because if you take the angle theta, it's always defined from 0, as we said earlier. 0 is the real axis, 0 degrees. But there's nothing stopping us actually starting at 0 and going around and going back again. And we arrive here. So what we're trying to say, I suppose, is that any angle theta in general can be thought of as also 360 plus theta. There's nothing stopping you going around and back to where you started. It's also equal to, you can go around twice. There's nothing stopping you going around twice. So it's 2 times 360 plus theta, etc. As a matter of fact, we can say in general that theta is equal to n times 360 plus theta, where n is the number of times you go around the circle. N could be anything from 0 upwards, basically. When it's 0, of course, it's theta itself. Excuse me. But you can go around 1, 2, 3 times, etc. There's no end to the number of answers you can have for theta. So that's the main idea that's different here. Or if you want to do it in radians, theta is equal to n times 2 pi, n times 2 pi plus theta, which is, and you can tidy that up as 2n pi plus theta. So this is a very important result from now on, that any angle can be written as 2n pi plus the angle, where n can be anything from 0 upwards. Or likewise, if you want to stay in degrees, you write it like this up here. And now we can go back to our polar form and we can rewrite theta to give the full picture of what's really happening at theta. So this becomes z is equal to r times the cos. So for theta, we're now putting in, we'll leave it in radians, 2n pi plus theta plus I sine 2n pi plus theta. So that's the big change here. We have replaced theta with the full version of theta, as it were, the version that you get when you keep going around as often as you want around the circle. So theta has become 2n pi plus theta, and that is the big change for general polar form. So we've now gone from polar form to what we call general polar form, as long as n can be anything from 0 upwards. So this is general polar form. Now, that's all there is to general polar form, really, in terms of the definition of what it is. However, we now need to do some examples and show you how that comes into questions. So let's start off with an example. So the example could be z cubed is equal to 1 plus root 3i. Solve for z. Now, to solve for z here, there's something different going on, because previously we used polar form when the power was over on this side. I mean, if the power was there, we had no problem. We used polar form. It turns out if the power is on the left-hand side, we have to use general polar form to get at all the answers, because if you look at this more closely, you can see what's really happening is the following. If we take both sides to the power of a third, if it's the power of 3 here, you go, if z is the power of 3, you go to the power of a third to cancel the 3. If that was z to the power of 4, for example, you'd go to the power of 1/4. But you must do the same on both sides. And the idea of that is to cancel the 3 to get what you're looking for, which is z. So we now have z on its own. Z is equal to 1 plus root 3 to the power of a third. And this is now a slightly different question to the ones we had where the power was a whole number, like 2 or 3 or 4, whatever. We did one earlier to the power of 10. When it's to the power of 10, etc., you use polar form to solve the question. But when the power is a fraction, like a third, we now use what's called general polar form. So this is a good rule of thumb for the exam. So this is the rule here. I'll just put it over here in red. If power is a whole number, use polar form. But if power is a fraction, use general polar form. So that's rule number 1, and that's rule number 2. And that's how you know in an exam situation which one to use. It's all about on the right hand side whether the power is a fraction or a whole number. So in this case, even though it started off on the left hand side as a whole number, what's important is how it ends up on the right hand side. And on the right hand side is a fraction, therefore we're going to use general polar form here. So now that you've got it written like this, we'll go through the steps. We'll write it in polar form first. So if we take that number inside the bracket now, take your 1 plus root 3i. Just look at that for the moment, that part of it. And what we're going to do is write it in polar form. So again, there's the a, there's the b. So in polar form, the modulus is equal to the root of a squared plus b squared, which is the root of 1 squared plus root 3 squared, which is the root of 1 plus 3, which is root 4, which is 2. And then the angle, of course, the argument of z theta, is the inverse tan of b over a, which is in this case the inverse tan of root 3 over 1, which is 60 degrees in the tables. That's a special angle, root 3. The inverse tan of root 3 is 60 degrees, or if you want to write in radians, pi over 3. So we have the two things we need for polar form now. So in polar form, the number becomes, so this number becomes r cos theta plus I sin theta, which is, we've now got r here. R is 2, and theta is pi over 3. So it's 2 times cos pi over 3 plus I sin pi over 3. So that's the first step, writing your number, converting it from Cartesian form, 1 plus root 3i, to polar form. Now that it's in polar form, we go on to the next step, which is general polar form. So you do it in stages. So now it becomes 2 times the cos. Well, for polar form, you put 2n pi in front, as we saw on the last page. So 2n pi, maybe make a square bracket to make it more legible, plus pi over 3 plus I sine 2n pi plus pi over 3. So again, in terms of steps for an exam situation, the first step is Cartesian. The next step is polar. And the next step is general polar. As you can see, it's getting a little bit more complicated each time. Now, don't forget the original question, of course, which is this thing we've been working out to the power of a third. This thing we've just worked out now inside the bracket, I should say there, 1 plus root 3i. This thing inside the bracket, 1 plus root 3i, is to the power of a third. So we now have to get all of that to the power of a third. So z is equal to all of that. So it's 2 cos 2n pi plus pi over 3 plus I sine 2n pi plus pi over 3. And the whole lot is the power of a third. So a lot of brackets here, so just take your time and be careful with brackets. So it's all to the power of 1/3. And we can split those up. The 2 is to the power of a third in front, and then the big bracket is also to the power of a third. So it's cos 2n pi plus pi over 3 plus I sine 2n pi plus pi over 3 to the power of a third. And now the next step is always to get rid of the power. So to get rid of the power, of course, we should also say at every stage where n, once you get the general polar, we should also say that n is equal to now upwards 1, 2, 3, etc. Now, the next step is get rid of the power, and we have a technique for doing that. We use the Marvers Theorem. So on the next page, let's just write down z one more time on the next page and show that step. So once more, z is equal to, what was it again, 2 to the power of a third times cos 2n pi plus pi over 3 plus I sine 2n pi plus pi over 3, where n, of course, is anything from 0 upwards. And it's to the power of a third. Now, the next step is to get rid of the power using the Marvers Theorem, so we'll do that. So it's 2 to the power of a third. That power now comes down in front of the angle. So it's a third, 2 to the power of a third times a cos. So the third comes down in front now. 2n pi plus pi over 3 plus I sine 2 a third is in front. We have to keep track of it all, so take your time with this step. So 2n pi plus pi over 3. So now what has happened is the power has come down in front of the angle. And we no longer have to worry about the power as such. And of course, n is from 0 upwards. N stands for the number of times you go around the circle. So that's the next step, which is the Marvers Theorem. I might put that in red actually, because we put our steps in red, so we'll just stay that in red for in terms of steps for the exam question. So the Marvers Theorem. Okay, and now that you've done that, the last step now is to basically fill in the numbers n equals 0, 1, and get your individual answers for z. So it turns out there are a few answers, there are a few solutions for z for this equation, and each time you put in a value for n, you get a different solution. That is up as far as 2. It turns out when it's to the power of a third, there are only 3 answers, the first 3, 0, 1, and 2, and then it starts repeating itself at 3. So if that was to the power of a quarter, for example, there would only be 4 answers. It starts repeating itself after 4, etc. So you only realistically you only need to put in the first 3 here. So now we get the individual answers by getting n n equals 0, 1. So that's a step in itself, filling in those. So don't lose sight of the big picture here. I've put the steps in red for the exam purposes because they're always the same steps. You go from Cartesian to polar to general polar, and then you use the Marvers Theorem to get rid of the power, and finally you put in the numbers one by one to get the individual answers for z. So put in n equals 0 first and see what happens. So z is equal to 2 to the power of a third times the cos of a third. Now if you put in 0 for n, you've 2 times 0 pi. So this is the n here, plus pi over 3. Plus I sine, same thing here, a third into 2 times 0 pi plus pi over 3. Now, of course, anything with 0 is gone. So it's a third by pi over 3, which is just pi over 9. So it's 2 to the power of a third times the cos of pi. A third by pi over 3 is pi over 9 altogether. Plus, so it gets much simpler now. I times pi over 3 threes is 9. So it's sine pi over 9. And then, of course, you can actually get the answer by, well, 2 to the power of a third, I suppose, is the cube root of 2, same thing. You can write that way if you like, cube root of 2. The cos of pi over 9, now you can get that on your calculator. So it's, if you change your calculator to radians, just do one here. So it's the cos of, pi, in a bracket, pi over 9. So let's just work that out. So it's pi over 9. So on my calculator, I get 0.9396, we'll say 0.9397. Plus I sine of that then. So again, sorry, that's just, we'll fix that. That's the wrong mode there, so we'll just try that again. So shift 4. So the cos of pi over 9, so it's pi over 9. Oh yeah, that was right actually. So it's 0.9397 plus I sine of that. So it's the sine of pi over 9. And 3420. That's really the answer. You can't do much more with that, really. It's an awkward decimal, so just leave it like that. If you like, you can multiply in, of course, the 3 root 2, the cube root of 2, and put all that in the calculator again. But the important thing is the method and how you go about doing this. So that's the first answer for n equals 0. So n equals 0. That's just the first answer. Now there are 2 more answers. So the next answer would be z is equal to the cube root of 2 again into the cos of, so once more it's a third times 2n pi, but n is 1 this time. So it's 2 into 1 pi plus pi over 3 and plus I sine, it's 1/3 again, into 2 n is 1 by pi plus pi over 3. And so that becomes, so that's n equals 1. Now, so z is equal to 3, the cube root of 2. So I'll just make that more clear that it's the cube root of 2 times the cos of, that's now 2 pi over 3 plus pi over 9. When you multiply by a third, plus I sine 2 pi over 3 plus pi over 9. And now you can get a common denominator. So it's a cube root of 2 cos, so the common denominator of 3 and 9 is 9, so it's 3 into 9 goes 2, 2 2s is 4, 4 and 1 is 5, so it's 5 pi over 9 plus I sine 5 pi over 9. And again, you can work that out in the calculator at this stage, or you can often leave it like that, depending on what they're asking in the exam. So that's n equals 1. And we've one more to do, then n equals 2. And it's the same procedure again. N equals 2. Z is equal to the cubed root of 2 times the cos of, it's a third into 2n pi, but n is, of course, 2 this time. 2n pi plus pi over 3 plus I sine a third into 2 by 2 pi plus pi over 3. And watch all your brackets again. So it's the cubed root of 2 times the cos of a third into 4 pi plus pi over 3 plus I sine a third into 4 pi plus pi over 3. And keep tidying up. So that's cos of, that's 4 a third into 4 pi over 3. We'll think of 4 pi as 12 pi over 3. It's 12 pi over 3. And pi over 3 is 13 pi over 3 altogether. Plus I sine a third times 13 pi over 3. And lastly then, it's the cubed root of 2. Make that clearly cubed root as opposed to 3 root 2. The cubed root of 2 times the cos of 13 over 9. 3 3s is 9, so 13 pi over 9 plus I sine 13 pi over 9. So they are the three answers. As I said, you don't have to go beyond n equals 2 because they start repeating themselves. You're backed into the same answer as n equals 0. And you can work all these out on the calculator, as I said. So to finish it off, just type them in if you like, or you mightn't have to, depending on what they're asking in the exam question. And that's the end of the section on general polar form.